SwayamPrabha. Digital India. Educated India.
Till now we had discussed aspects about solid rockets, liquid rockets and hybrid rockets. Now let us look at how to determine its performance. We had talked about this, that we need to understand equilibrium calculations in order to get to know what is the composition of the gases in the rocket motor, and then we need to look at what happens when these gases flow through the nozzle. Remember, initially when we discussed about nozzle flow, we had said there are two assumptions that are possible. One is equilibrium assumption, wherein we assume that there is sufficient time for the reactions to take place, and because of which if you look at the temperatures that are achieved inside the nozzle, because there is a temperature and pressure decrease, certain kind of exothermic reactions are favored, and you will get a better performance if you have equilibrium conditions. And if you have the other condition, that is frozen condition, that is the composition is frozen at the entry to the nozzle, then you will get a slightly inferior performance, right. We can examine those things here with this software called NASA SP273. Earlier it was written in Fortran language, and it was used as such with input file. Currently there is a front end available to it, and it is called a CA software, which you can download from the internet. It is freely accessible, and if you download this software, you will find that it has a manual, and it has all the other input files, example input files that are there. Now if you look at the folder in which it is there, you will have something known as CAEXC win, which if you double click, you will be able to open this software. This needs a Java platform to run on. Okay. Now if you open this, this software is a more generic software. It can solve many kinds of problems. One is the rocket problem that is of interest to us, that is here. Then in addition to that, it can solve the combustion problem, that is if you are holding internal energy and volume constant, then assign temperature and volume being constant, then enthalpy and pressure being constant. That is, if you are only interested in looking at the combustion chamber of a rocket motor or a gas turbine engine and what are the temperatures that are achieved and other things, then you can use this. Again, you have assigned temperature and pressure. It can also do the shock tube problems and many other problems. Now let us in this case look at only the rocket problem, because that is of interest to us. So you have to firstly click on this rocket problem. Now this menu opens up, wherein you can define whether you want equilibrium or frozen flow conditions in the nozzle. You can click for both, because the actual situation will be somewhere in between equilibrium and frozen flow. So you have to give the chamber pressures as an input. So let us say firstly we have to, before we go there, we have to as I said earlier, there are example problems. So firstly let us look at the example problem that is there, that is example 8, which is stated as a rocket problem. Okay. Now here if you look at this, This is an example problem. The initial pressure is set as 53. We can change that to something like 100 bar. Okay. You can input at one time many more pressures, 150 bar and 200 bar. Okay. You can also have different units in which these can be expressed. We will click both equilibrium and frozen, and for the exit you can either define a supersonic area ratio or in terms of pressure ratio. So, we will define in terms of area supersonic area ratios, that is 25, 50, 75, and lastly we will define something like 100. So, and finally you have to save this. Once you save this, because this is a liquid propellant problem, you have to define the oxidizer to fuel ratio, right. There are different ways to give that. One is equivalence ratio is also possible, then oxidizer to fuel ratio is possible, then percentage of fuel by weight is also possible. So, let us click on the oxidizer to fuel ratios. There is one set value that is given here, that is the value at which probably you will get the best performance. Okay. Now, let us also click other O by F ratios. Remember, we are doing this problem, the reactants are, if you click on this reactants this thing, you will get fuel is liquid hydrogen and oxidizer is liquid oxygen. For stoichiometric conditions, the O by F should be 8. So, which is why I have clicked 8. Now, because these are already there in the menu, so the temperatures automatically come in and the heats of formation are also automatically taken in. Okay. Now, if you click on this, if you click on the name and if you check something as take something as a fuel, and if you click on that, you can change it from liquid hydrogen to something else also. And there are a few options that are available here, like methane, then there is kerosene, JP4, JP10, all this. Then there is also RP1. Okay. We will right now stick to what is been selected, that is liquid hydrogen. Okay. And you have liquid oxygen. As I said again, you can click on this and select any other oxidizer. There are various options here that you can look at, that is H2O2, H2O2, then RFNA, IRFNA, then N2O4. Okay. So, and also liquid oxygen. So, we will go with liquid oxygen. So, both of them are 100%. You can define whether you want liquid oxygen as 50%, some other oxidizer as 50%, that is also possible. So, we will save this, and what you have to do is you have to go to this activity and click on the execute CA. So, if you do that, it will execute the program and give you an output file in this fashion. You can also open this output file as a Word file. You can open it as a notepad or a word pad. Now, if you look at the output, it firstly tells you what are the input conditions that you have given, the O by F ratios. Okay, you have chosen equilibrium and frozen, and what are the pressures, what is the pressure ratios that you have looked at, and supersonic area ratios, what are the reactants, and what is the units in which the output file is expressed in. So, now if you scroll down, you will get huh? Is it okay? So, if you look at the output file here, you will find that firstly the O by F ratios that we have chosen are indicated here. Then we have set both equilibrium and frozen flow. Then the various pressures at which we want to run this calculations, those are given here. Then the exit pressure ratios, supersonic area ratios and subsonic area ratios, and then what are the reactants that we have used, and the outputs will be expressed in SI units. Now, if you scroll down, this is the place where you will have the results. What you can see here is fuel and oxidizers are given, the energy, the heats of formation are also given here. Now, we will take the case when O by F is 5.55 and the pressure is 100 bar. This is what we had given. Now, look at what happens to molecular weight. This column here is molecular weight. Now, the molecular weight is somewhere around 12.8. Okay. So, and the temperatures you get are given here. This is in the combustion chamber. So, this is around 3450 almost, and this is the throat region. As the flow expands, the temperature drops, so also the pressure drops. Okay. And further, as you go to different area ratios which are given here, this is AE by AT. If you use a 68 AE by AT, then 1.58, 25, 50, 75 and 100. So, you can see that both temperatures and pressures keep dropping after the chamber depending on what we have as the area ratio. Okay. And what this also will give you is specific impulse and vacuum specific impulse. So, you can see that the vacuum specific impulse is always going to be higher than the specific impulse. This specific impulse is at sea level, okay, wherein the ambient pressure is 1 atmosphere. So, you see that at sea level with an area ratio of 68, you will get something like 4384 Newton second per kg. Okay. It is seen as meters per second here, which is the same as Newton second per kg. So, the ISPs that you get are very high. Okay. If you use a larger area ratio nozzle, you will get even higher specific impulse. That is what you will see here. As you change the area ratios, the specific impulse also will increase. You also can get C star values which are shown here, okay, and correspondingly CF values. So, you just have to multiply C star into CF to get ISPs. This also gives you, as I said earlier, that if you look at the exhaust, it will have various species. So, the species that are there are HO2, H2, H2O, H2O2, OH and O2, and the corresponding mole fractions are given here. Okay. You can see that large fraction is H2O, okay, and there is quite a bit of unburnt hydrogen, right. So, this constitutes roughly 95% and the remaining 5% is contributed by the other species. So, these are the two major species, okay, in the chamber as well as in the exhaust. Now, this was with equilibrium, right, and you can see that if you look at the composition, right. Let me first go back and check whether this is equilibrium composition. At this at some values the frozen flow does not give the correct composition. Okay. Now, take a look at the ISPs. Let us take this last two values. We will take a look at only the vacuum specific impulse. This is roughly 4600 at 100 area ratio. Okay. Now, if we do a frozen flow analysis in the nozzle, it reduces to 4425 at the same conditions of AE by AT. So, it is very clear that the actual one will probably lie between 4425 to 4600. Okay. So, the actual ISPs that we get will be somewhere between this. This was for 5.55 O by F. Now, if you look at O by F of 1, okay, the temperatures that you get are very low, right. So, therefore, the ISPs that you get are also not very large, 3632 and 3700 at area ratio of 100, and vacuum specific impulse is 3825. Although the molecular weight in this case, because the O by F is 1, right, we need a higher O by F to completely burn it. O by F of 8 is required. If we use a very low O by F, as you can see here, molecular weight is also very low. Although temperatures are lower, molecular weights are also lower, but still, as C star is nothing but under root T c by m, we finally will get something like 3600 seconds. And then if we increase the O by F to 2, then the temperatures rise, but so also will the molecular weights, and as a consequence you will get to a slightly higher ISP of 4249. Okay. Then if we go to an O by F of 3, temperatures go to 2450 and molecular weights increase to something like 8. So, consequently, ISPs go to something like 4469. Then further, if we increase the O by F to 4, this goes to 4569. Okay. Five, it becomes 4475. Here in this case temperatures are increasing, but molecular weight is also increasing. So, therefore, the ISP change is very small, and the best is probably at somewhere around 5.55. 5 you get 4603, okay, and 5.5 is where you will get the best ISP. This is for liquid propellants. The same information is shown here in this graph here, which shows on the x axis chamber pressure and ISP on the y axis. There are two ISP graphs here. One is ISP at sea level, which is indicated by this blue line, and there is ISP vacuum, which is indicated by this red line, which is usually higher. Both these are for the hydrogen and oxygen system at an O by F of 5.55, and at all these pressures the area ratio of the nozzle is such that the flow is optimally expanded. Now, one can see that as pressure increases, the ISP also increases, both the sea level and the vacuum ISPs, both of them increase. Now, to understand why it is that we choose an O by F of around 5.55 for the hydrogen oxygen system, we have plotted here chamber temperature, C star and molecular weight. Molecular weight is in blue color, that is this line. Chamber temperature is in red, that is this line, and C star is shown here in this green line. This is at different O by F, and the flow is optimally expanded for a pressure of 70 bar. That is, the area ratio of the nozzle is chosen such that flow is optimally expanded. Now, if you see at around 5.5 is where chamber temperature is also high, molecular weight is also not as large. So, you will find that the C star values are very good. Now, with these C star values, if you multiply it by the CF, which is a function of nozzle area ratio and pressure ratios, you will find that you will get a very good ISP at around 5.5, which is why most rocket motors which use hydrogen oxygen combination operate around this oxidizer to fuel ratio. Now, here I have compared hydrogen and oxygen and kerosene and oxygen systems. The red line here is the variation of kerosene oxygen with chamber pressure. This is ISP, and this is sea level ISP, wherein with increase in pressure the flow is optimally expanded. That is, the area ratio is so chosen that at each and every pressure here the flow is optimally expanded. One can see that when we change from kerosene to hydrogen as the fuel, the ISP is much higher with hydrogen as the fuel compared to with kerosene as the fuel. This is because one, the molecular weight of hydrogen is much lower, and therefore, you will find that the C star values for hydrogen systems will be larger than what you would get with kerosene, and therefore, you get a very good specific impulse with hydrogen and oxygen systems. And if you look at the sizing of the overall system, it depends on the O by F at which it is operated. If you see here, oxygen, hydrogen and oxygen systems are shown here. This is with different oxidizer to fuel ratio and ISP on the y axis. The red line indicates kerosene oxygen, and the blue line indicates hydrogen and oxygen, and the chamber pressure is 70 bar, and the flow is optimally expanded. So, you find that you need a O by F of around 5.5 to get a very good specific impulse, whereas with liquid oxygen and kerosene you need somewhere around 2.5 to get a very good specific impulse. We will now look at a solid propellant. The example 5 problem here deals with a solid propellant, but the binder is something different. So, we will take a look at another example wherein I have looked at HTPB as the binder. Okay. Now, if you look at this, there is 68% ammonium perchlorate, 18% aluminum, and then 14% HTPB. Now, as I said, if these compounds are not found in the list, you have a provision here to indicate a name and then amount and what temperatures and energy, and you can also provide a chemical formula here. I have taken a butadiene formula here, C4H6, which is very good approximation for HTPB. HTPB will have an OH radical in the end of the chain. Even if we neglect it, it does not matter as much to what we are doing. So, here what we have to click is, for a solid propellant it does not everything is preset. In some sense you just have to define what are the percentages, and that should automatically take care. Therefore, we do not have anything clicked in this menu here, and if we click at the rocket menu, we have something like at 70 atmospheres and 70 pressure ratio. We can also give something like 10 and 15 area ratios. So, we click both equilibrium and frozen flow. So, now if we look at the output file, you have 70 bar as the pressure, area ratios, and then the various components, that is ammonium perchlorate, aluminum, and HTPB, which is 14%. So, now if we look at what happens, 70 atmospheres, the temperature is very high, but because the molecular weight is also quite high, you end up getting an ISP of around 257 seconds. This is with equilibrium calculations. With frozen calculations it will be even lower. Sometimes this frozen calculation does not work beyond the throat, because if you have more of alumina, then it does not work for the frozen flow, because it then becomes a two phase problem. Okay. You are looking at if you look at what are the temperatures, this is lower than the alumina melting point. So, it will be a two phase problem, and therefore, the frozen flow will not be able to solve for it. Now, one can also look at this is with if you lower the pressure to something like 6 bar, okay, you notice that these temperatures are also not very high, because the if you look at equilibrium, pressure is also something that determines what is the equilibrium composition, and therefore, the temperatures will depend on what is the pressure. So, you will get a lower temperature and correspondingly a lower ISP. Right. What this software will not be able to tell you is look at the ISP column with 15 area ratio and with 6 bar, right. So, the pressures, if you are doing this experiment at sea level, the exit pressure is very low, right, and in this condition you will have probably a normal shot sitting in the divergent portion of the nozzle, and therefore, you will not be able to get these kind of ISPs, but unfortunately this software will not be able to tell you that. So, one needs to be careful and look at the exit pressures while doing this. If you are doing sea level operation, you need to be careful about what is the exit pressure and use the Summerfield criterion, which is something like 1/3 of the exit pressure is what it can take without any problem. Okay. Now, one can also change the, remember we said if we make this aluminum is added only to enhance the specific impulse. So, let us say we make it 0% and this 86%. So, ammonium perchlorate and binder only. So, then if you run the So, it is reduced because aluminum content is not there. Look at the other thing that the temperatures here you get is lower, molecular weight is also lower, but in that case the temperature was higher and molecular weight was higher by, it went up to something like 27. So, therefore, this was around 3400 and this was 27, therefore, you ended up getting a higher specific impulse. Okay. Now, solid propellants, we had just now seen how its ISP varies with pressure. Here we have plotted pressure on the x axis and ISP on the y axis, and at each and every pressure the flow is optimally expanded, that is again the area ratio is so chosen that the flow is optimally expanded, and the red line indicates a non-aluminized propellant and the blue line indicates an aluminized propellant. It is very obvious from this graph that for an aluminized propellant the ISP is always higher, because with the aluminum combustion the chamber temperature is always higher, and therefore, you get a much better ISP compared to a non-aluminized propellant, and also both of them tend to increase with increase in pressure. Anyway, we will go to liquid hybrid propellants. Now, hybrid propellants, as I said, we can look at HTPB binder and liquid oxygen as oxidizer. Okay. That is what we have selected here, liquid oxygen 100%, HTPB binder 100%. Okay. Now, we need to also give O by F ratios. So, we can give something like 1, 2.2 roughly is where you will get the best performance. So, if you look at the pressure, we have given something like 200 here, let us lower it a little to 100, and supersonic area ratios ranging from 30 to 60. Now, if we open the output file, so O by F ratios ranging from 1 to 3, and we also have 2.2, and fuel is HTPB, oxidizer is liquid oxygen, and pressure 100 bar and area ratios. We see that at O by F of 1, the temperatures are very low, and as a consequence you will get something like 260 seconds or 274 seconds with vacuum ISP. Now, if you go to higher O by F, at 2 the temperatures increase and also the molecular weights will increase, and as a consequence you will get something like 327 seconds sea level ISP and around 340 seconds vacuum ISP. Okay. Then if we go to something like three, then you get these kind of numbers. Okay. The temperatures has increased, but molecular weight has also increased. Okay. Now, you can play around with the kind of additives that you would want to add. Let us say I talked about aluminum hydride as a possible additive that can increase the specific impulse quite a bit. So, we will select aluminum hydride, it is already there. I just need to put something like 50% aluminum hydride and reduce the binder content to something like 50%. So, overall the binder and the fuel binder and aluminum hydride put together is 100%. So, now if we run this, here you see we have added aluminum hydride, that is around 50%, and binder has been reduced to 50%. Somewhere around 2, the temperatures are very high, and so also the ISP is high, 341 seconds, and vacuum ISP is 361, right. And at an O by F of 1, it is 351 and 367 seconds. You see here, as O by F is reduced, the molecular weight is getting reduced and the temperatures are also smaller, but what we are interested in is a combination, and therefore, we end up getting a better performance at this O by F. Okay. Now, if you go to an O by F of 3, the molecular weight has increased to something like 30, and the chamber temperature is 4000, but the ISP you will get is lower. Okay. So, with aluminum hydride it offers you can also change the fraction of aluminum hydride and find out where you will get the best performance. What we have probably selected is not the optimal. So, you can play around with it and find out at what fraction you will get a better performance. Aluminum hydride is a good additive to add, because it can then increase the specific impulse, and if you look at the specific impulse with HTPB and LOX, as I said earlier, this is very similar to what you will get with kerosene LOX, but if you want to go beyond that, you have to use something like aluminum hydride, which will increase the specific impulse even further. Here there are two hybrid systems that are compared. On the x axis you have chamber pressure, and on the y axis ISP. The red line is for aluminum hydride and HTPB, 50% aluminum hydride, 50% HTPB, and liquid oxygen. The blue line is for liquid oxygen and HTPB. The O by F is 2 for the blue one, and the O by F is 1.3 for the red line, that is aluminum hydride propellant, and in all these cases the flow is optimally expanded. Now, if you see here, with aluminum hydride being added at the expense of HTPB, we do tend to get a very good specific impulse, and this tends to increase with pressure. So, there is a difference of around 20 seconds in ISP between these two. So, adding aluminum hydride is a very good thing. It will help in increasing the ISP. Again we are comparing aluminum hydride propellants with HTPB and O2 propellants. This is again a hybrid rocket. Here we plotted with O by F and ISP on the y axis. This is for a chamber pressure of 70 bar, and again the flow is optimally expanded. What we see here is another interesting feature. The red line is for aluminum hydride and HTPB combination, and the blue line is for hydrogen HTPB and oxygen system. Now, if you see here, the peak specific impulse is achieved with aluminum hydride propellants at around 1, whereas it needs to go to somewhere around 2.2 for HTPB and O2. What it indicates is that if you use aluminum hydride, you will get a much smaller or a much more compact system with density impulse being higher, because the O by F at which the best specific impulse is achieved is at 1. Usually liquid oxygen, which has a density of around 1140, has lower density compared to the solids, and this here has a density of around 1200 to 1300. So, therefore, you will get a very good density impulse, and this makes the systems smaller. So, you can, as I said, play around with this and try and generate your own numbers. One way to check whether you have done something correctly is look at literature. If you do a solid propellant, what are the ISPs to get, and then find out if you redo the same, will you get the same. So, and then you can, once you get the confidence, you can play around with this and look for other additives and things like that. Okay, we will stop here. Thank you very much.